Hello and welcome to another lecture of classical motion of a single particle. So, as we are discussing the Newton's law of dynamics and its different applications, we start from one dimensional motion. We said that we realized that a very simple Newton's law can be used to find different information related to the motion of a single particle. We also introduced the concept of integral of motion or the constant of motion. We saw that when the force is 0, then the the linear momentum is vectorially conserved, because ddt of mv is f. When f is 0, ddt of mv is 0. And then also we said that if we have for example, we did that for one dimension. Let us say if we have a 0 force, then we have a trajectory which is linear, and this is a trajectory with uniform velocity. We also said if the force is non-zero but constant, then we can expect a parabolic trajectory. We actually will encounter, and actually we encounter such type of constant force every day while we are talking about the Earth's gravitational pull on us. Because g, the gravitational acceleration is constant, and for a particle of mass constant, effectively the force is actually constant. Now, we also said that if we take the force to be of a very specific kind, where f can be written as the minus of the spatial derivative of a scalar function v, then this quantity half m small v square plus v is a constant of motion in 1D. We also said that if f is a function of v, and actually more precisely when f is equal to kv with k to be negative, okay, then this type of force can cause the kinetic energy to decrease with time. On the other hand, if k is greater than 0, then we have an increase in kinetic energy. Okay. So, such terms can be used to model viscous force or sometimes the energy pumping in a system. Okay. We then said that in 3D this type of conservation of energy is also true, and there you have to guarantee that the force, the vectorial force, should be in this form minus nabla v, where v is another scalar function which is a function of x, y, z, and nabla is nothing but a partial differential operator on the space variables. I can write like this: x cap plus del del y, y cap plus del del z, z cap. When I say nabla of v, we call that as also gradient of v, which is nothing but equal to this, and here you can just put your v, okay, and that gives you actually a vector. Now, you see, if you have this, then even in 3D or even in more than 1D, you have half mv square plus v x y z is constant. Remember, at this point this v is no longer dx dt, this v is modulus of v vector, which is nothing but dx dt x cap plus dy dt y cap plus dz dt. I should write like this. I am just thinking of a little bit. Yes, I can write like this, I think. Yes, z cap. Yeah. Okay. So, this is the v vector. Okay. Now, so whenever I am saying, so what is Vx? Vx is nothing but dx dt, and Vy is nothing but dy dt, and Vz is nothing but dz dt. Okay. And what is then V? So, V is nothing but then root over Vx square plus Vy square plus Vz square, that much we have. We will see a very interesting relation which will be actually very useful for the systems where you are not considering a single particle. So, it is not exactly beyond I mean in general lying in the scope of our course now, but it is when you are talking about a rigid body, a rotation, spin, for this type of thing this concept will help. I am now going to explore that part. Okay. So, for that part you have to start from this m r double dot is equal to f. This is a symbol I am now introducing deliberately. When I am saying r dot, this is simply meaning ddt of r vector. Okay. Anything. So, for example, just a scalar phi, if I say dot, it means d phi dt, the total differentiation of phi with respect to time. Okay. If I say r double dot, then it simply says d2r dt2. So, here I can easily write like this. Okay. If in both sides you do something m r cross r double dot, then here it will be r cross f, then you can write this as m r cross r double dot plus you can write something which is actually 0. So, you can always add a 0. So, you can write like this m r dot cross r dot, and which is equal to r cross f. This is actually 0 because two vector, the same vector cross product is always 0. And then you can say, look, if it is, if I put this in a compact form, this is ddt of r cross r vector, sorry, r cross r dot vector, which is equal to r cross f. And what is r dot vector? This is v vector. So, I can take m inside because this is just a constant. So, ddt of r cross mv is equal to r cross f. So, you see, let us say your f is not 0, but your f is somehow proportional, I mean f is somehow parallel to r vector, then r cross f is 0, and then you have a new conserved quantity. So, if f is parallel to r, then r cross f 0 and your r cross mv is a constant of motion. This quantity is known as angular momentum. Okay. So, this is another conservation quantity, conserved quantity, another conserved quantity, and you again see that in this conserved quantity you do not have, although this is a vectorially conserved quantity, it does not have the time explicitly appearing. So, this is also an integral of motion in a sense. Okay. Now, this quantity is known as the torque, r cross f. Okay. So, we actually say that just like the force is the rate of change of the linear momentum, the torque is the rate of change of the angular momentum. Okay. So, just like linear momentum is at the base of any linear type of motion or like translational motion, angular momentum is somehow at the basic level of any type of rotational motion. Okay. So, you will understand this when you will go a little bit like more advanced topics in classical mechanics. Okay. I will now do another thing. So, some conserved quantity under some other conditions. So, let us say I have another situation, I have m and dv dt, and which is nothing but equal to f. If that f is of this form, it can be of this form, which is like f is equal to velocity vector cross another vector. Now, if you have the idea of true vector or polar vector and pseudo vector and axial vector, you will understand that f is always a true or polar vector, and that is why, and v is also a true or polar vector. In that way, b must be an axial or pseudo vector, okay? Otherwise the parity wise change is not satisfied. So, so if you really search in nature, you will actually see that such a force is actually possible when your b is the magnetic field, okay, and there is a proportionality constant which is given by the charge of the particle. So, this is the motion where we are just talking about the motion of a charged particle with charge q, okay. And if a particle is is having a charge and like having some non-zero velocity, then in a magnetic field it has a force acting on this particle, which is v cross b, okay. Your m dv dt is equal to some q v cross b, let us say. Can you easily see a very easy, very evident conserved quantity? So, I just do m v dot dv dt, q v cross b dot v. When I have at least two of the three vectors to be identical in a scalar triple product, I have a 0 result over here. So, it is a 0. So, that means d dt of half m v square is 0 and half m v square is conserved. So, you see that this force, this type of force actually can conserve the kinetic energy itself, okay, whereas a force of type like this would require a second component of energy, which is the potential energy, to be conserved, okay. Now, at this point I would like to introduce two identities, vector identities, okay. So, as a prerequisite, I was just requiring vector algebra and not vector calculus. That is why you will also see that in the first tutorial, assignment 0, I actually gave you problems on vector algebra. So, vector calculus I will somehow introduce in this lecture step by step as necessary in a very brief manner, okay. And so, as we already have introduced gradient or the the nabla operator, and now this nabla operator is a vector operator. So, just like a dot b and a cross b, nabla operator can be actually used to define these two quantities, nabla dot a and nabla cross a, where a should be a vector, and since this is a partial differential operator, so if it is written like this way, then actually this is nothing but del a x del x plus del a y del y plus del a z del z. So, that means the x component of this nabla operator would exactly contract with the x component of a, and y component would contract with the y component of the delta operator, or the del operator, or this nabla operator would contract with that of a, that is the y component, and the z component of this nabla operator would contract with that of that means the z component of a. Okay. So, this is simply this, and this is a scalar. On the other hand, this one is tricky, and this one is actually like a cross product. So, this is a vector, okay, once just like this is a vector, and of course, just you calculate the the cross product between two vectors like a determinant of a matrix. Here you can do the same thing, but you just have to do like this ijk del x, del y and del z, then you will have ax, ay and az. Okay. So, if you do that, then what will be the ith component? The ith component will be del az del y minus del ay del z. What will be the jth component? So, I just write one by one. So, curl of A will simply be equal to del az del y minus del ay del z I cap or x cap, whatever, I cap, x cap, y cap, j cap, I will use somehow equivalently. So, please bear with that. Then for j, I would have del ax del z minus del az del x y cap plus finally del ay del x minus del ax del y z cap, or sorry, I mean I have already mixed it. You see I just write here, yeah, j cap and k cap, yeah, okay. So, that is what it is, okay. So, you always have to do this cross multiplication in a proper order, and so for k I would say this is del ay del x minus del x del y, correct, yes, that is true, yeah. Now, you see I will do two important results here and which we will need very well. So, okay, before that let me just give their names to us. So, this one is known as divergence of A or the divergence of the vector field. So, here it is divergence of A and this one we call as curl of A. Sometimes we also say rotational of A, okay. So, or curl of A simply, okay. Now, I will do some important things. First, let us just realize two things. One is divergence of R vector. What is this? So, in 3D space, this is nothing but del x I cap plus del y j cap plus del j k cap dot x I cap plus y j cap plus z k cap, and if you do the contraction it will give del x plus del y plus del z which is equal to 3, and this is nothing but the number of the dimension. If you are in an n dimensional space, then divergence of R will be n, okay, number of dimensions of space. What is curl of R? That is somehow very important or also interesting. So, you have to write I, j, k, you have to do del x, del y and del z, then you are writing x, y and z, and then you do like I. So, x, y, z, all of them are mutually independent. So, that is why when you do this partial derivatives, if they are independent and explicit, there is no explicit dependence, the partial derivatives are 0. So, so for example, when I say what is del z del y, that means what will be the change in z if I change y keeping z and x constant. So, I am keeping z and x constant. So, what will be the change in z? When I just change y, it will be 0, because I say keeping z and x constant, that is by the definition of this partial derivative, okay, and that is why this will be 0. On the other hand, in the same way this will also be 0. So, it will be 0 minus 0, and if you see carefully for the all other coefficients, I mean all other components, for z it will be 0 because del x del z 0, del z del x 0, and finally same for the kth component, which is del y del x and del x del y, both are 0. So, finally you see curl of R is a null vector, okay. then I will do other two things. First is curl of a gradient of a scalar. So, this type of thing already we have seen while we were talking about the conservation of energy, then the force had to be on this type of, had to be in a form like this. Okay. Now, what will be this? So, this phi can be arbitrary scalar, okay. But if I take a curl on the gradient of a scalar, then I j k del del x del del y del del z, what will be the x component of del gradient of phi or nabla phi? That will be del phi del x, and same for the other two components del phi del y and del phi del z. So, what will be the ith component? Ith component will be del 2 phi del y del z minus del 2 phi del z del y. Now, you see for a scalar function, okay, which is just a normal scalar function, these two things they are always equal, okay, and that is why they vanish. On the same by the same reason you can also say the other two components are also vanishing. You can do that explicitly, and that is why this one is equal to 0 vector, another null vector. Okay. If you now calculate at home and check that if you do divergence of curl of any arbitrary vector, it will also come out to be 0. Okay. For that you just have to use the definition of divergence and curl properly. So, the curl of A you can calculate by this, and then you have some vector, okay, and then you have to perform this divergence, and you will see that this will give you a 0 scalar. Okay. So, if you do all these things, then you can actually think of something that if I have if I have a force field or a vector field which is in this form, then the curl of this will be 0 because of this identity, right. And that is why we say that if the force sometimes, instead of saying that if the force has a form like minus gradient of phi or plus gradient of phi, if we say that okay, for a particle which is moving under a force whose curl is 0, then for that particle the mechanical energy, the total mechanical energy is a constant of motion. Okay. Now, I know that if f is grad phi, then curl of f is 0. Is the converse true? Can we show that? Actually, we can show that. In the next lecture, I will do that systematically. Okay. That means, if grad curl of f 0 is equal to 0, then this one I know, if this, then this is correct. Then can I say f is equal to, f is equal to gradient or minus, just minus is for like convention, so that you have half mv square plus something, okay. Otherwise you will have minus something, okay. Is this true? That I will show in the next lecture, okay. The last topic for today's lecture is to understand a little bit more about this kinetic energy. I already defined kinetic energy as half mv square, but you can also see directly from the Newton's second law a much more physical interpretation for kinetic energy, and for that what you have to do is this. Okay. which actually says m dv dt, m dv dt is equal to f. You can take just like the previous time, you take m v dot dv dt is equal to f dot dr dt. I am just taking the dot product with v, so because v is dr dt, I can write this, and then I can simply say m v dot dv. I just take the dt out. I just now write simply this m v dot dv is equal to f dot dr, and this is nothing but d of m v dot v by 2 or v square actually, is equal to d of, I can write that like I have name w, which is not a scalar state function. Okay. So, I can just write this, but this is not an exact differential. That means, if you just integrate this, if you just integrate dw between some point 1 and 2, it will simply not be w2 minus w1. That is not possible for w. Okay. So, I can somehow name this like this. Now, you see that this simply says that this quantity, as we know, this is by concept is the work done on the system, okay, and this quantity is what I call the kinetic energy. So, any change in the kinetic energy is equal to the change in the work done. So, will it be if I now do something, that will be actually much more easier to understand. If I now integrate them from some initial step to the final step, then I can say that this is nothing but half m Vf square minus Vi square is equal to some delta W. Then I can say that the work done during this process, while this particle is moving from velocity Vf to velocity Vi, if the work done is in this process, if the work done is given by delta W, then that will be exactly equal to the change in kinetic energy of the particle. So, kinetic energy in a sense can be thought to be a source of work. Okay. And if you now see this philosophically, it simply says that somehow kinetic energy and work, one can be converted to the other, like one can be used in the other form like that. Okay. And this is the famous Wrok-energy theorem in classical mechanics. Okay. Now, you see the interesting point is, as I said, dw is equal to f dot dr, and which is not just as not an exact differential, but if f is of this form minus gradient of phi, then what is this? What is dw? I just did this calculation some while ago, and this is nothing but minus of d phi. So, you see, although in general this is not an exact differential, but under the condition where f is minus gradient of phi, your dw is an exact differential. Okay. So, once again, and this is true when your f is having 0 curl. So, in a way it is correct to say that if the force field of my system is having a 0 curl, then the force field can be written as a gradient of a scalar function or minus of a gradient of a scalar function, and then as a result the total mechanical energy of the system remains constant in time, and also the work done between two states, initial and the final state, does not depend on the path chosen, but it simply depends on the initial and the final state. Okay? And such force fields are known as conservative force field. So, a force field, sometimes when I ask students that what is a conservative force field, they say this is a force field whose curl is 0 or something like that. So, at the fundamental level, conservative force field is a force field which conserves the total mechanical energy. Okay? The traits are like it is irrotational, it can be written in the scalar of a, as a gradient of a scalar function, and the corresponding work is can be written as a state function. So, the incremental work done is an exact differential. All these things we can do, but the fundamental thing is a conservative force field is one which conserves the half mv square plus v, the total mechanical energy, kinetic plus potential. Okay. So, you see all these concepts basically makes the building blocks, all these concepts actually together make the building blocks of the understanding of the classical mechanics of a particle. Now, before ending this lecture, so the scientific topic wise I wrap up this lecture here, but I will just do a small comment and small exercise. So, that is also easier. So, as I said that whenever your function is, whenever your force is in this form like this minus gradient of phi, then you know that this dot dr or I would say f dot dr. So, I can write a little bit more properly. So, I can write. So, okay, I can present like that if this is followed, then if I give you the potential function, you can simply take the partial derivatives, you can calculate the gradient and you can tell me the force. Now, is the other way is the other way is easy as well. That means, given the force function, can we also find out the corresponding phi, and also it is also important that can we at all verify that whether there is at all a potential function associated with this. In other sense, given a force field, can I check whether this force field is conservative or not? All these questions can be answered if you can calculate the phi, corresponding phi. And just as you know that f dot dr then will be simply equal to minus gradient of phi dot dr, and by definition this is nothing but minus of d phi. Then if you just have your force field, you dot with dr and you just cast the whole thing as d of a function, then you are done. I am just giving you a small example, and with that we will end this lecture. Okay. So, let us say my force field is 2xy plus z cube I cap plus x square j cap plus 3x z square k cap. Now, I have to find the phi. So, for that the first thing I can do is like this, f dot dr is equal to, so 2xy plus z cube, it will be contracted to dx, then plus x square will be with dy plus 3x z square will be with dz. Okay. Now, this is something your high school exercise in casting different expressions, differential expressions as exact differential. So, as you can just see that if I just take this 2xy dx plus x square dy aside, and then I take plus z cube dx plus 3x z square dz separate, then this part I can simply see that 2x dx is nothing but d of x square. So, y is there, so I write like this and then I write x square dy. Then I can also write z cube dx plus 3x, I mean instead of like this I can write x 3z square dz, I can write d of z cube. Then I know this is the formula like y dx plus x dy, which is d of x y. So, here it will be d of x square y, and this is the same thing here, it will be d of x z cube. So, it will be d of x square y plus x z cube, and hence, so phi will be equal to minus x square y plus x z cube plus some constant of integration. Okay. Now, you start with this expression and you take the gradient of this f, you will have this. You can check another interesting thing, you can directly calculate the curl of this force field to check. So, that is I leave up to you, check if curl of f is 0 or a null vector or not. Okay. So, with this thing I am just wrapping this lecture up, and in the next lecture we start the several okay, we will first demonstrate the proper demonstration of this if vector is curlless, then it can be expressed as a gradient of a scalar, and then we will go to a very interesting topic, which is the topic of the central force. Okay. Thank you very much.